Hello everyone, my name is Moritz Nottebaum and I'm going to present our work, Efficient Feature Extraction for High-Resolution Video Frame Interpolation. This is a joint work with Stefan Roth and Simone Schaubmeier. In this work we aim to perform efficient video frame interpolation. Given two subsequent video frames, the goal is to generate several intermediate frames. Recently, the highest interpolation quality has been achieved with neural networks. Often they consist of a sequence of modules targeted to different steps. The first step extracts a suitable feature representation from the images, from which the motion between the two input frames can be predicted, for example in the form of optical flow. From this, the final intermediate frame can then be estimated in an image synthesis module. Overall, this can result in a quite complex network design, with many parameters. This becomes especially obvious when we visualize the required computational resources of existing methods for processing high-resolution 4K videos. We plot here the required GPU memory versus the number of trainable parameters of some recent methods. The lower and the more to the left, the more efficient a method is in terms of computational resources. We can see how with our proposed method we can lower these requirements significantly. In this presentation, we will describe our main design choices, as well as show that the perceptual quality has not been sacrificed. We achieve these results by carefully designing the general overall pipeline, with a focus on keeping the computational cost low. Our main contributions are twofold. We first propose an efficient feature extraction module, which takes inspiration from classical approaches of linear dimensionality reduction. Second, we design the rest of the pipeline in a very lightweight fashion, with a focus on using non-learnable fixed computations where possible instead of large neural networks. We start with our main contribution, the efficient feature extraction. A common method for feature extraction is to pass an image through several convolutional layers to obtain a compressed feature representation. The dimensionality can be reduced, for example, with strided convolutions. However, CNNs are very costly processing 4K images. Compared to HD images, processing 4K resolution requires 4 times the computation and memory. On the contrary, in order to make the feature extraction more efficient, we make use of the principle of linear dimensionality reduction. Specifically, we propose a discriminatively fine-tuned linear dimension reduction module, FLDR in short. As a result, our approach only needs one FLDR layer to extract the relevant information, which is needed in further parts of the framework. Like any layer in our model, the FLDR is fine-tuned end-to-end. Our fine-tuned dimensionality reduction is inspired by block-based PCA, which we summarize here. For block-based PCA, we divide a frame into different blocks of equal size. Then we compute the PCA representation for that frame, where each block represents a data point. After that, we transform each block with only a limited number of components, namely the largest eigenvectors. The resulting representation is a very efficient image encoding, holding most of the information of the frame with fewer coefficients. By only using the first 16 components for each 8x8 block, we achieve a compression ratio of 1/4. We use here the color blue to highlight that these operations are fixed, in the sense of non-trainable operations. Drawback of PCA is, however, that it is computed without the task of frame interpolation in mind. As a result, it is data-specific and not task-specific, unlike a learned convolutional neural network. We therefore propose to fine-tune the original computed parameters to make them task-specific. More specifically, before we start our training, we take a random image from the training dataset and apply a block-based PCA transformation. We then use a portion of the eigenvectors and the mean vector to initialize the parameters of the dimensionality reduction layer. After the initialization step, the mean vector and the eigenvectors are treated as trainable parameters, which are optimized for the task of frame interpolation. Next, we describe our motion estimation module. For motion estimation, we use a multi-scale architecture to first estimate the bidirectional flows between the two input frames. In terms of trainable parameters, this is our most expensive module, containing 80% of the parameters. However, in the end, we need the intermediate flows pointing to and from the intermediate time step t. Computing the forward flow from the input frames to the intermediate time step is easy and can be achieved by scaling the predicted flow between 0 and 1. Computing the flow for backward warping is more complex, as we need to compute the flow starting from the unknown pixel positions at the intermediate time step t. This can therefore only be done in an approximated way. We decide to not use the neural network for this in favor of keeping the computational resources low. Instead, we approximate the intermediate flow from t to 0 and t to 1 directly by warping the scaled bidirectional flows accordingly. Given our 4 intermediate flow fields, we can warp the input frames to the intermediate time step t to get 4 different candidates of the intermediate image. However, these intermediate images often suffer from different artifacts. Next, we discuss how we can obtain the final interpolated image. A common approach to generate the final image is to either combine the forward warped images or the backward warped images with an occlusion mask and add a residual image to it, which is estimated by a costly synthesis network. However, we observe that the weighted combination of the intermediate warped images and the input images already gives a high-quality interpolated frame. In order to combine 6 images, our occlusion mask is 3-dimensional and normalized with a softmax along this last dimension. The reason for that is that we thereby have a convex combination of pixels for each output pixel. In order to combine these 6 images, we use a lightweight occlusion estimation network, which estimates the weighting factor for each image candidate. To summarize, we are able to significantly reduce the computational costs. To highlight this, our complete pipeline has less than 1 million parameters, even for 4K images. Let us break this down. Our linear projection vectors only have about 1,000 parameters. Our motion estimation, with more than 700,000 parameters, is our largest module. A lean design of the image synthesis module contributes 200,000 further parameters. To evaluate our network, we tested on 4 different datasets of videos at 4K resolution. We visualize here their different characteristics by plotting the different percentiles of motion magnitude between the input frames. Datasets with larger motion magnitude tend to be more difficult. However, XTest contains a lot of camera motion, leading to large dominating flow magnitudes, but of lower complexity. XIF4K and XTest are commonly used datasets for video frame interpolation. However, both only contain a few scenes and test frames with limited variability. We therefore created 2 additional test sets with about 1 order of magnitude more evaluation scenes and frames, as well as moderate motion distribution. Even though the motion is generally lower than for XTest, the quantitative evaluation of the various methods on these 2 new test sets show that they are more challenging. In the following, we show some quantitative comparisons on 2 of the datasets. First, for XTest, the test set which has been introduced alongside the method XVFI and contains a lot of large motion. We achieve state-of-the-art accuracy on XTest among models without pre-trained flow. Our approach also has the lowest memory requirements and the lowest number of trainable parameters among all approaches. When looking at our new test set Inter4KS, which has many more test frames than XTest, we can observe an overall lower performance. Our approach ranks first with a small lead among compared approaches. We even slightly outperform M2M PVC, despite not using any pre-trained flow and requiring half the memory. Let us now look at the importance of the various components in our overall framework. Without fine-tuning the projection vectors of the linear dimensionality reduction, our model performs far worse. The same applies when we only rely on the forward flow. Both changes lead to a considerable drop in PSNR on both test sets. As stated before, we refrain from using a synthesis network, as it is costly in parameters and memory. That said, including a synthesis network only improves the performance on some test sets. Qualitatively, our approach is better at interpolating large object motion in 4K video frames. Both Rive and M2M PVC create more intense ghosting. Here you can see the whole scene from the last slide in motion. We show 8 intermediate frames for 2 input frames. Our interpolation also works well for small objects with small motion, where for example M2M PVC on the top right loses the details in the interpolated frame. Minor and diverse motion is similarly well handled by our approach, as by the more memory-intensive models. In this talk, we introduced fine-tuned linear dimensionality reduction as an efficient way to extract features for optical flow estimation and showed that task-specific fine-tuning leads to performance gains in video frame interpolation. A carefully designed framework is overall lightweight in terms of computational resources, while achieving comparable or even superior performance than more expensive models. The code, pre-trained model, and the used test sets are publicly available on our website. Thank you for following our talk. We hope that you have enjoyed it.